You ever just stand at the edge of the ocean and watch the water? It really does feel alive, doesn't it? Like it's breathing in and out with this rhythm that feels ancient and just, well, unstoppable. But what's actually going on under the surface? What are these incredible invisible forces moving all that water across our planet? Well, today we're going to dive right in and unravel the science behind the ocean's pulse.
So here's our game plan. First, we're going to get the language right. Then we'll look up to the stars for the main cause. After that, we'll see how things get a little messy down here on Earth, make it all practical with a really cool analogy, and then we'll wrap it all up with why this stuff really, really matters.
I mean, it's one of nature's most reliable patterns, isn't it? That water level just creeping up the beach and then slowly pulling back out. Twice a day, pretty much like clockwork. It feels so predictable, but the mechanics behind it are this fascinating cosmic dance of physics. And this shot right here, it just perfectly captures that heartbeat. You can literally see the water level changing so dramatically against something fixed like a lighthouse or a cliff. This constant up and down motion is the foundation for everything we're about to talk about. But to really get it, we need to make sure we're all speaking the same language.
Okay, first things first. We have to get our terms straight, because in science, words really matter. You hear people use terms like tide and current all the time, almost like they're the same thing. But nope, they describe totally different phenomena. And understanding that difference, well, that's step one.
First up, tide. The most important word here is vertical. A tide is simply the rise and fall of the sea level. It's the water going up and the water going down. That's it. Simple, right?
Okay, so if all that water is moving up, it has to come from somewhere, right? And when it moves down, it has to go somewhere. That in and out movement, the horizontal flow of water that's created by the tide, that's called the tidal stream. So here's the key. The vertical tide causes the horizontal tidal stream. One leads to the other.
But hold on, because there's another kind of horizontal movement. This is a current. Now, unlike a tidal stream, a current has absolutely nothing to do with gravity and the tides. It's driven by other huge forces, like massive persistent winds, or even differences in water temperature and saltiness that create these enormous river-like flows right in the middle of the ocean.
So if you're on a boat, what do you actually feel pushing you around? That's what we call water flow. It's the grand total, it's the whole shebang, it's the tidal stream that's caused by the tide, plus the underlying current that's caused by the wind and weather all mixed together. This is the net effect, what's really happening on the water's surface.
And this little table is perfect. It just lays it all out for us nice and neat. See? Tide is vertical, caused by gravity from space. The tidal stream is horizontal, and it's caused by the tide. The current is also horizontal, but it's caused by wind and other stuff. And the water flow, that's just what you get when you add those two horizontal movements together. A great little cheat sheet. All right, now that we've got the vocabulary down, let's zoom out. Way out. Because the ultimate reason for the tides isn't on Earth at all. It's happening out in space, in this constant, really elegant gravitational ballet between us, the moon, and the sun. And it all boils down to one word: gravity. You know, Isaac Newton figured out that every object with mass pulls on every other object. The sun pulls on the Earth pulls on the moon, and, most importantly for us, the moon and sun are constantly pulling on Earth's oceans. Now, the moon is so much closer to us, so its pull is the strongest. It literally tugs the water on the side of the Earth facing it into a bulge. But here's the wild part. It also pulls the Earth itself away from the water on the far side, which creates a second bulge over there. So as our planet spins, we pass through both of these watery bulges each day. And that's why we usually get two high tides. Okay, so if it's all just based on the super predictable orbits of the moon and the sun, we should be able to predict water movement perfectly, right? Should be easy. Well, this is where the nice, clean cosmic model runs smack into the messy reality of planet Earth. Just look at the difference here. On the left, a tide table. It's precise, it's mathematical, and it's incredibly accurate for predicting that vertical movement we talked about, the tide. But on the right, that's a map of the actual water flow. It's complicated, it's messy, with arrows going in all sorts of directions. So predicting the time of the tide is one thing. Predicting the actual movement of the water is a whole other ballgame. So why is it so messy? Well, it's because of all the local stuff happening right here on Earth. Strong, steady winds can literally just push water around, completely changing its speed and direction. the shape of the coastline, the depth of the seafloor. That all creates friction, slowing water down. And like we said, big differences in temperature and saltiness create their own powerful currents that get mixed in with everything else.
Okay, I know this all might seem a bit abstract. So let's make it real. How does all this stuff actually affect something moving on the water, like a boat? There is a fantastic way to think about this. This is it. This is the key. Forget all the complicated physics for just a second and picture this. The surface of the water you're on isn't standing still. It's a giant moving carpet. And this image explains the idea perfectly. Look, the boat is moving forward on its own power, right? From its engine or its sails. But at the exact same time, the entire carpet of water is moving sideways. So the boat's actual path over the ground is the combination of those two movements. You could be steering straight ahead, but that water flow is carrying you completely off course. If you navigate, understanding this is, well, it's everything. So let's bring it all home. We've gone from the gravitational pull of the moon, way out in space, all the way down to the practical reality for a sailor sitting in a cockpit. So why does getting this stuff right matter so much? Because these forces can be mind-blowingly powerful. Take the Baltic Sea, for example. After a long stretch of strong southerly winds, the water literally piles up in the north. When that wind finally stops, all that water rushes back south, creating a current of up to 7 knots. That is over 8 miles an hour. For many boats, that's faster than they can even travel. This isn't just a tiny detail. It's a dominant, powerful force that you have to respect.
So the next time you're near the ocean, just stop and watch the water. See if you can spot the difference between the steady rise and fall of the tide and the horizontal rush of the water flow. Think about the moon way out there, pulling all that water towards you, and the wind and weather adding their own chaotic signature. You're not just looking at water anymore. You're witnessing this beautiful, complex symphony of forces that spans the entire solar system.